So we spoke about two problems. One is the problem related with the coefficients, or the other is the problem related to the r squared. Now we can sort of make a sense that it is a problem of overestimation or underestimation, and we'll try to sort of interpret from the numbers whether the problems of overestimation or underestimation, and we'll try to make sense from these numbers. So let me first write down the coefficient value. Let's say in my actual model, so I'll write down the values actually. Actual model, so my beta 2, that is, or b2 rather, so actual model I can write beta 2, no problem. So beta 2 is equal to something like 0.18, right? Beta 2, let me just go back there. Beta 2 is this is a real model. I have educational experience 0.18 and experience is 0.02. 0.18 and beta 3 is equal to 0.02, and the fitted model 1, where I only had my b2 is around 0.16, and fitted model 2, where I only had my b3 is equal to something like 0.008, let's say. Now essentially, of course, we see that this is, if I compare these, so b2 is an underestimation of beta 2, and here also b3 is an underestimation of beta 3. Okay, so it's a b3. Now why exactly it is happening? So remember the relationship between education and experience that we have defined in our data. So if we go back to that do file, you will see experience and education, they're actually negatively related. Okay, so education and experience, they're negatively related. So if one is increasing, the other is decreasing. So what is happening here is that we have this H, which is basically the relationship between education and experience, that is negative, whereas the beta 2, that is the coefficient of education, that has a positive contribution towards wage, and beta 3, that is the experience, that is a positive contribution towards wage. But because H is negative, so when we have this, if we consult this table, beta 3 and H, so if one is negative and the other is positive, so then, or rather in our case, this is the case. So if one is positive and the other is negative, so what we are going to have is a problem of underestimation of beta 2 here, right? So exactly that is what we see. So how would it make sense is that when I am, let's say in this case, when I'm omitting experience, so that actually undermines the coefficient of education, because they are negatively related. So it is cutting down. So when B2 is actually capturing a part of education, because they're negatively related, a part of it is actually, sort of cutting away. And similarly for experience. Now because experience and education are negatively related, so the moment I remove education, so what is happening, a part of it is actually cutting away from 0.02, it is becoming 0.008. So that is what we have to sort of keep in mind. Okay. Now what about the r squared term? Now r squared, in this model, r squared was 0.45. In this model, r squared was 38, and in the third model, r squared was 0.008. Okay. So if I add these two things, I will get, if I sum it up, I will get 0.39, which is less than 0.45. And how do I explain that? How do I remember the fact that r square is proportional to the correlation coefficient between two variables? Okay, we have seen that previously. So r square is equal to r square. We have actually derived that at some point. Now r square is related to the correlation coefficient, and again beta beta is related to the correlation coefficient because we know that beta is nothing but r sy by sx. So that is something we sort of get for simple OLS, and because of this we can say that r square is actually proportional to beta. Okay, so beta is a coefficient. Now because of this relationship, if I have an increased value of beta, it is also going to contribute to the r squared. Okay, so now that the r squared value in these two models are actually the beta value in these two models are actually small, so what you are going to have, a corresponding r squared value is also going to be relatively smaller. But whereas when I have in the first model, true model, I have my beta values higher, and naturally the r corresponding r squared value is going to be higher. Of course, about this is the explanation of both the questions. Now you can actually do this work even further. I mean, of course, I have kind of claimed that my model is correct only when I sort of include experience and education both. But it can also happen that I can say, okay, it is not enough. I have to have the experience squared along with the experience. Okay. Now, if I want to include experience squared, and that is actually what the Mincerian wage regression is, now then I have to go to the next block of codes, and I can actually see that in this case I have these three regressions, and in this case this middle regression is going to be the true equation, and the first and third are actually not going to be the right representation of the equation. Okay, so they are like omitted variables. So in the first case I have omitted the experience squared, and in the second case I have omitted the experience. Okay, and we can see actually the consequences of such omission. And let me actually run the regression so that we can actually get a sense. So let me actually include the experience squared term here, and let's see what is happening. So if I run this, I get this regression equation where my adjusted r square value is pretty high, 0.467, and I have all these coefficients, experience squared, as I said that it is essentially representing the tapering off of the wage with experience, and that happens because with ages, as we increase, as we get old, our experience starts counting less. So that is why this negative coefficient. So normally what happens is experience squared is going to contribute wage in negatively. So essentially the beta 3 is going to be negative, or here in this case beta 4. So let me actually write down the equations. Let me actually write down the equations. In this case, the true equation is going to be wage, or log of wage, let's say, is equal to, let's say, beta 1 plus beta 2 into edu, beta 3 into experience, beta 4 into experience squared, and then I have some error term. Okay, what is my fitted model? ln wage. I'll consider the fitted models where I'll consider actually two fitted models. So let me write it down. So in this case, in the first case, I will actually omit the experience squared. So ln wage is going to be, let's say, b1 plus b2 edu and b3 experience. I do not have experience squared, and I have a fitted model. And the next fitted model, I'll have, let's say, I'll omit the experience, rather I'll have experience squared. So ln wage is going to be, let's say, b1 prime plus b2 prime edu. I'm keeping edu in both the equations. And then I've omitted the experience part, so there is no b3, and then I'll have a b4 experience squared. Okay, so this is how I have sort of written my equations. I'll also add another equation which will show at the end of it what happens if I have, let's say, b1 double prime, b2 double prime, or actually we'll not have any edu, and let's say we'll only have b4 double prime experience squared. Okay, so I'll just come to that to explain the r squared part. Whereas this fitted models, let's see what is happening to the coefficients, fitted 1, fitted 2, and fitted 3. Now let us look at these equations in my do file. So let me go to the do file, and in the do file I can see that in the last block of equations I have general education experience, experience squared, and I have only taken experience squared. I'll just add one more here. And that is basically I'll keep general education and experience squared. Gen edu and experience squared. Okay, so let me run the regression. So this is the main equation. This is the actual equation, true equation. And if I run it, what I'll see here is this equation. Okay, so I see that experience squared is negative, experience is positive, general education is positive, just the way we have expected. Now, interestingly enough, previously my experience coefficient was 0.02, but here I see 0.05. Okay, so that is interesting. And let's say I run the other regression equations. So let's say I take fitted 1, which is general education and experience, and once I run it, let's see what is going to be the outcome. So result is CUC. We have done it previously. So if I have only experience, I have 0.02, whereas in the previous case I have seen 0.05. So basically when I include the experience square, the coefficient for my experience is actually increasing, just like the previous case. And if I run the regression where I have only, let's say, general education and experience squared, what we'll see here is that my experience square has become positive instead of having a negative value. And how do I explain in both the cases? So let me explain the first case first. So let's see what happened here. So what happened in the first case is that the moment I included experience square, my experience has increased. The coefficient for my experience has increased. And why is that? Because experience square is a negative. So beta 4 is negative in this case. So let me actually write it down. So beta 4 in this case, let me actually go to the whiteboard. Beta 4 in this case is negative. Beta 4 is negative. Whereas H for experience and experience square is of course positive. It is positive. So the moment I'm excluding beta 4, so what I'm having is that beta 4 and H, that together they're giving me a negative sign, right? The resultant of this is going to give me a negative sign, and that is being captured in the experience. And what is happening? It is undermining the coefficient of the experience. Okay, exactly what you have seen previously. Okay, so this is a case where we can say we are having something like this. Okay, so here my H is negative, H is positive in this case, and my beta 3 is negative in this case. Okay, so essentially it is an underestimation problem, and that is exactly what you see in the result. And what about the last part? So if I go to the last part where I had in my regression, I have actually omitted the experience part. Rather, I have kept the experience squared part. What is happening here is, again, the experience is being captured by experience square. Now experience is related to y positively, whereas experience square is related to y negatively. Okay, but the net effect, because the experience has a much higher impact on y vis-a-vis the experience square, that is only has a role have a role in tapering the whole income experience curve. So here we will see a net positive. Okay, and that is basically an underestimation of the experience square, because that is being impacted by experience here. So that way we should understand how the variables are related within themselves and how they're related with the y. Okay, so that's how we should understand. Now let us look at the r squared part. The last part here is the r squared part, and in the first model we sort of had both general education experience square, and sorry, in the first model we had general education experience, and in the second model we had general education experience square. So we cannot really add these things up this time because in both the cases we have general education, so it is being captured. But what we can do instead, we can, in one of our models, we can actually omit the general education altogether, and we can capture it only once, and that is in this equation. In this equation, equation 3, we have basically omitted general education, and we have captured only experience square. So if I add this 3 with 1 and see what happens to the r squared and compare that with 2. Okay, so basically what I want to do is r square in 1 plus r square in 3, and I'll see how it is related to the r square in 2, because r square in 2, that is going to be my true r square here. Now if I look at the r square value, and if I just go back to my Stata results, and if I look at the r squared value, what I'll see is I will see, okay, I have to run this once. Let me run this. Let me go to the do file and let me run this, the last part of the do file. So that is this one. Okay, only this is my equation 3. So here I have my I'll show you this. Here I have my r squared value is 0.0013, and in the previous case where I had general education and experience, I had 0.45. So if I add these two things up, I'll have, back to the whiteboard, so r squared, or rather r squared 1 is going to be, or r squared 3 is going to be 0.0013, and r squared 1 is going to be 0.45, and my r squared 2, where I have included all these explanatory variables. Let me actually go to the file here, Stata file, and here I will see when I have all the variables, it is 0.467. So let me write it down here. 0.467. Now if I add r square 1 and r square 3, I will see 0.45 plus 0.0013. It is going to give me something like 0.45. Let me actually reduce the size a little bit. It is going to give me 0.4513, which is actually less than 0.467. So exactly what you have seen previously. In the case of underestimation, since the betas are actually, the r square is actually related to the betas, the value of the beta, so what is going to happen is we're going to see an underestimation of r square. So even if we add these two r squared values, they are not going to give me, or they're actually going to be less than the true model, the r square corresponding to the true model. So this way I will ask you to also see those cases where my h is positive, where my beta 3 is positive, and then if I actually run the regressions, I will see r square 1 or for fitted, and r square for fitted 2, If I add these things up, we will actually see that it is going to be r square true model. Okay, because here we'll see overestimation of beta, and therefore correspondingly an inflation of r square value, and that is, if we add these up, they're going to be bigger than, let me actually show you. Yeah, they're actually going to be bigger than the r square value corresponding to the true model. So with this, we sort of end this lecture here, where we have explained the impact of omitted variable bias on r square. Thank you.